The interpreter pattern defines a way to represent and evaluate sentences in a language by using an abstract class for expressions which concrete subclasses implement to interpret specific parts of the language's grammar. So the interpreter pattern is probably the most complex and least used of the gang of 4 design patterns, and most courses on design patterns that I've seen don't actually include this interpreter pattern. However, at the beginning of this course I promised that I'd teach you all 23 gang of 4 design patterns, so let's give it a go. And after the example that we're going to go through, I'll also discuss why this pattern is rarely used. So here are some example use cases for the interpreter pattern. So it's used in parsing and executing SQL queries, where the interpreter pattern helps to parse the query syntax and execute it against a database. It's used in calculators or scientific software that interpret and evaluate complex mathematical formulas entered by users. It's also used in web frameworks that render HTML templates with embedded expressions or directives. So for example, templates in web frameworks such as Laravel or Django. And for example, in Laravel you have the Blade templating language where you can sort of write your variables within curly braces. It's also used in JSX and React, and then that is parsed by some parser and turned into or interpreted into some sort of HTML template. So let's say that we want to build a calculator app that takes some user input string and calculates the result. So here we have a user input string, so we have 1 plus 2 times 3, and an interpreter needs to convert or parse this input or expression into an abstract syntax tree or an expression tree. So you can see here that an expression tree looks something like this. It's kind of like a tree of a tree structure of objects. So you can see here 1 plus 2 times 3. We can't simply just go from left to right. We can't say 1 plus 2 and then times 3. We've got to respect maths rules, so the BODMAS rules, which mean that we have to perform the multiplication first and then we have to add the 1. So we have to do 2 times 3 and then add 1 to that result. So 2 times 3 is 6, then we add 1 to get 7, and that's the result of this expression. So when we build the abstract syntax tree, we need to respect BODMAS, so we need to get the order of operations correct. So you can see here we first of all have an addition expression which contains 2 more expressions. Okay, so you can see the first expression we do is the multiplication expression, which is the 2 times 3. So we can see here we do 2 times 3, and then finally we add the 1 onto that result. So essentially what we're doing here is we are converting or parsing an input string into a tree of objects according to the grammar rules that we specify, and in this case the grammar rules are the sort of maths BODMAS rules. So the result of the expression that we have here can be found by calling its interpret method. So on this expression tree, all expressions will have an interpret method, and we can call this and it will find us the result of this expression, which we know is 7. So we can essentially use the interpreter pattern to get from the user input to create this abstract syntax tree, which can then be interpreted or evaluated to get the result. So here are the components of the interpreter pattern. So we have abstract expressions which establish the interface for all expressions within the language. So the abstract expression is essentially going to be an interface which has an interpret method that all expressions will implement. So in our case, all the expressions that we have, the concrete expressions, are the addition expression, the multiplication expression, and number expressions, and all of these implement this I expression interface, and will have an interpret method which defines how these expressions should be interpreted. We then have terminal expressions, which represent the fundamental components of a language, such as numbers or variables. And in this above example, number expression is a terminal expression or a leaf that represents integers. So you can see here we have number expression where you pass a number of some sort, and we can pass either a string or an integer in our case. and this can be when you call the interpret method on a number expression object, it will just return an integer value directly. So in this case, if we pass 2 as a string, it will return 2 as an integer, and in this case it will return the integer of 3. Okay, so they can be interpreted directly, basically, these terminal expressions. We then have non-terminal expressions, which represent more complex expressions that are composed of other expressions using operators or functions. So above, the addition expression and the multiplication expression are non-terminal or composite expressions. So this means that the non-terminal expressions are built up of sub-expressions. So you can see here we have a multiplication expression, which is built up of multiple expressions. It's built up of 2 number expressions, and we can see here the addition expression is also built up of 2 expressions. We have this multiplication expression and we have this number expression. So you can see here, if we call the interpret method on a non-terminal expression, then it can't be directly interpreted, because if we look at this multiplication expression, it first of all has to interpret this number expression, then it has to interpret this number expression, so it has a left and a right expression, if you will, and then it has to multiply these results together. And you can see here this addition expression first of all has to evaluate this multiplication expression, which has to evaluate these number expressions, and then once this is evaluated, it has to evaluate this number expression. So non-terminal expressions can't be directly interpreted like the terminal expressions. They essentially have to be recursively interpreted. We have to recursively keep on calling the sub-expressions interpret method until we finally get to the results of the terminal expressions. And then we also have an interpreter which implements the logic for interpretation and determines how to evaluate different types of expressions. So I'm fully aware right now that you have no idea what is going on, so we're going to go through an example, and it will definitely help if you try to code this example out a few times. So first of all, we're going to create a context class that is going to contain any global information needed for interpretation. So let's create that context class. So in our case, for our simple calculator example, we don't currently really need this context class. But say that we wanted to interpret English language into Spanish, and each Spanish-speaking country speaks Spanish slightly differently. So this context object or class could contain the country and city that we are currently located in, and it could also contain the gender of the person that we are speaking to, as that could also affect the interpretation. But for now we're just going to leave this as an empty object. So next up, we need to create the abstract expression interface. So we're going to call this iExpression, and each expression needs to have an interpret method where we pass the context to that method. So each expression will have access to any context data. So next up, let's create our first concrete expressions. So first of all, we're going to create the terminal expressions, and in our case we just need one, and that is number expression. Okay, so this needs to implement the expression interface. Okay, so it's going to have an interpret method. So in number expression, we need to provide a number when we create a number expression. So let's create a number field, which is going to be of type integer, and then we can create a constructor. So we're going to create a number expression constructor which takes in an integer number, and we can assign that to our number field. And what we'll also do is we'll overload the constructor. So we're actually going to copy and paste this constructor down, and we can also provide a string number. And then what we can do is we can convert this string number. So if somebody creates a number expression object and passes a string, then we're just going to convert this string into an integer before assigning it to the number field. So this just makes this class a little bit more flexible because we can provide both integers and strings. Okay, so finally in our interpret method, because this is a terminal expression, we can just return the number. Okay, so that's very simply what number expression does. Okay, so next up we can create our non-terminal expression. So first of all we will create our addition expression. So let's go ahead and create that. And this needs to implement the iExpression interface. Okay, so if you remember, non-terminal expressions are composite expressions. In other words, they are built up from multiple sub-expressions. So what we need to do here is let's create two fields of type expression, and we're going to have a left expression and we're going to have a right expression. So in addition, for example, if we have 1 plus 2, then the left expression would be a number expression where we pass 1, and the right expression would be a number expression where we pass 2. And then we can interpret both of those expressions and then add them together. And that's what we're going to do in our interpret method. But first of all, we actually need to create a constructor or some way of setting these left and right expressions. So let's go ahead and do that. And we can assign the fields in the constructor. So next up, we need to actually interpret these expressions. So we're just going to say left dot interpret, and we pass in the context, and then we need to add the right expression interpreted. So again, if these are number expressions, they will just interpret to their integer values and then they will be added together. Okay, so that's what we have there. So next up, let's create another non-terminal expression, which is the subtraction expression. So subtraction expression, and in here again we're going to have a let's see, where are we? So let's copy and paste these two fields in. I'm also going to copy in what we have from addition expression, and we're just going to modify things a little bit. So this needs to be subtraction expression. So the constructor, we set the left and right expressions, and then in interpret, rather than adding them together, we are subtracting them. Okay, so finally we're going to create a multiplication expression. So again, this is going to be very similar to what we have in the addition and subtraction. Okay, so again we're going to have two fields, and we're going to set those expressions inside of the constructor. So let's see, let's copy and paste that in, change the name of the constructor, and this needs to also in fact, we forgot to implement the expression interface here, so let's implement that in the subtraction expression, and we also need to implement it here in the multiplication expression, and then implement the interface, and then here we're just going to return the left expression, and then we're going to interpret it, pass the context, and then we're going to multiply by the right expression. Okay, so that's everything that we need for our expressions. So next we need to create the interpreter, or the parser class, which needs to convert some input string, for example 1 plus 2 times 3, and it needs to convert that into an abstract syntax tree or an expression tree. And first of all, so let's go ahead first of all and create this interpreter class. So the interpreter is going to hold a reference to the context. Okay, and it's also going to have an interpret method which interprets the expression or builds the expression tree. So let's create that method. It's going to return an integer. In other words, the sort of final result from parsing the expression. So this needs to take a string, an input string or some expression string. You can call that whatever you want. And what we're going to do is we're going to build an expression tree. So we're going to create a separate method for building the expression tree. So we're going to call this build expression tree, and in here we're going to pass the expression that we want to build an expression tree from. And then finally we're just going to return the expression tree, and we're going to call the interpret method on that tree and pass in the context. Okay, so that's going to return an integer value. So let's now create this build expression tree method, which is going to return a expression, and it's going to take some input. I'm going to call it input, you can call it expression, whatever you want. So this is where things get a bit more interesting, because building a parser that converts some input strings such as 1 plus 2 times 3 is actually pretty complex, because we can't just sort of traverse this from left to right. We have to perform this 2 times 3 first and then add the 1. So building parsers are complex, which I'm going to show you very shortly, and it's very easy to get them wrong. So for simplicity, we're just going to skip this building an actual parser for now, and we're just going to hard code in the expression tree for the input 1 plus 2 plus 3. And of course in the real world you would need to build an actual proper parser or download one from somewhere, from some package. So let's actually hard code in a few things here. So we're going to say the input is always going to be 1 plus 2 times 3, and we're then going to hard code our expression tree. So we'll say expression tree is equal to, and what we're going to do is we're going to build an expression tree for this particular input example. So first of all we have to do the addition expression, and inside of here we need to first of all do the multiplication expression, which is 2 times 3. So we do a new multiplication expression, and in here we can pass in the number expressions of 2 and 3, and we can pass 2 in here, or it can be a string, and we do new number expression 3. Okay, and then we also need to then add this 1, so we do new number expression and we say 1. Okay, then from here we can return this expression tree, okay, which is going to be interpreted in this interpret method. Okay, so now let's have a look at how a client would use this solution. Okay, so let's say that we have an input string of 1 plus 2 times 3, and in this case it doesn't actually matter what our input string is, because we've hard coded the result in here. We've hard coded the input and we've hard coded the result of this input example. I am going to show you how to build I'm going to show you what an actual parser for this would look like and how it would build this expression tree from this input. But for now, let's just hard code things in for simplicity and for a little bit of sanity. So we can then create our context object, and we can create our interpreter, and we pass in our context object. Okay, so let's actually get the result from interpreting this input. So we can say interpreter dot interpret, and we can pass our expression, our input expression, and we can assign this to a result variable, and let's actually log this result to the console. Okay, so let's log this. We should get 7 back, because 2 times 3 is 6 plus 1 is 7. So let's see what we get, and we will get result equals 7. Okay, so that is all looking good so far. Next up, I'm going to show you what an actual interpreter class would look like if we actually parsed the input string correctly programmatically. So let me now show you what an interpreter class would look like if it actually parsed the input string into an expression tree. And for simplicity and a little bit of my own sanity, the interpreter only handles addition and subtraction, as handling multiplication, division and brackets in an expression would require quite a bit more complexity. For example, 1 plus 3 times 4 requires the 3 times 4 to be executed before adding the 1 due to BODMAS. So creating language or grammar parsers is actually very, very difficult to get right. Even for this simple parser that I'm going to show you now, it only actually handles addition and subtraction. I've not actually handled multiplication and division, and it's still fairly complex. It still takes quite a bit of thought to build out, and it's very easy to get wrong. So what I'm actually done here is I've already built out this second interpreter which actually parses the input string, and it's exactly the same as the interpreter that we built before up until this build expression tree method, where we actually now have an algorithm to parse the input. Okay, so we can see here this only handles addition and subtraction. So first of all, what we do is we split the string into a list of tokens, or an array of tokens. So you can think of tokens as like the words in a sentence, or in our case the tokens will be the operands and the operators. So the operands are these numbers and the operators are like the addition and subtraction signs. Okay, so we build up a list of tokens by splitting the string via the spaces. We then create an output queue and an operator stack, and this is pretty complex and way beyond the scope of this course to actually go through what is going on here. This is a course on design patterns, not on algorithms, but essentially what we're doing is we're using an algorithm called the shunting yard algorithm to change the sort of format of our expression so that we can build an expression tree. And you can see here, depending on the token, we are creating new expressions of certain types. So here, if it's a plus sign, then we sort of add to the stack an addition expression, and we add the left and right expressions that we need to add. Okay, so it's pretty complex, and I don't want to go through all of this, and it's way beyond the scope of this course, but I just wanted to show you that even for just having a parser that handles addition and subtraction, it's actually very complicated. And if we wanted to actually account for multiplication and division and brackets, then it would be even more complex. So I just wanted to show you basically that building parsers is extremely difficult to get right, and yeah, it's something that you're not going to be doing too often in your life as a software developer. At least most of you won't be doing that anyway. So let's actually use this in the client now. So we're going to change the input. We can't do multiplication with this one, so we're just going to do let's see, 2 plus 3, and then we'll minus 4, and we will add 10. So this should give us a result of 5, 1, so it should be 11. Okay, that's what we are expecting, and we're now going to use interpreter 2 instead of interpreter 1. Okay, so that should all be okay. So let's run this, and we should get 11. And as you can see, we get 11, so that's all working correctly. So what is actually going on here? So let's sum up what we have so far so that we can better understand what is going on here. So first of all, we have the client, our sort of program.cs file, which initiates the interpretation process by providing first of all an input expression to interpret, and it also creates the interpreter object and the context object with information that is needed for the interpretation process is passed to the interpreter, and in our case we are not providing any context data. Okay, so next of all the parsing and building of the abstract syntax tree. So the input expression is turned into an array of tokens in the interpreter. So if we go up here, we can see we're turning the input into an array of tokens, and tokens are analogous to words in a sentence, and these are parsed via some algorithm. So we have our big algorithm here that creates an expression tree that represents the input. And if we go into our first interpreter, the expression tree will look something like this. It builds an expression tree that sort of represents our input. Okay, so each operator and operand, so the operators being like the multiplication symbol or the addition symbol, and the operands being the numbers themselves, are each represented by a corresponding expression object. So the numbers are represented by the addition expression, and the operands are represented by the multiplication expression, or the subtraction expression, or the addition expression. Okay, and they're basically built of sub-expressions. Okay, so let's now have a look and have a think through the expression evaluation. So we've built our expression tree from our user input. Now we need to interpret this expression tree. Okay, so the interpreter, so if we go into this interpret method, we first of all create the expression tree, then we have to interpret it. And the interpreter traverses the expression tree and interprets each individual expression or node as it goes. So for terminal expressions, the operands or numbers such as 1, 2 and 3, their interpret methods directly return their numeric values. So if we have a look in the number expression, you can see number expression is just returning the numeric value. And for the non-terminal expressions, the operators such as plus, minus and multiply, their interpret methods call their left and right sub-expressions, and then it calls these left and right sub-expressions recursively, and then performs their respective operations, so either add, subtract or multiply. And what we mean by recursive, if we just have a look in here, you can see that we first of all have to call this addition expression. We call interpret on this, and then from in here we call interpret on this multiplication expression, and then we have to interpret this left expression, then the right expression, then we multiply them together, and then we have to interpret this number expression, and then we finally add them together. So we're recursively calling the interpret method on each of these expressions as we traverse the expression tree. Okay, so then we need to combine the interpreted results. So the interpreter combines the results of the sub-expressions according to the defined grammar rules that should be represented by the expression tree. And in our example, following BODMAS, 2 times 3 should be performed or evaluated first, and then we then add on the 1, so that the final output is then returned to the client. So here is the Gang of 4 UML for the interpreter pattern. So you can see here we have our abstract expression interface with an interpret method that takes the context object, which contains some sort of data that is relevant to the interpretation. And then we have our 2 groups of expressions. We have terminal expressions, which basically kind of return the building blocks or the kind of fundamental sort of words or digits in our language. So in our case that was just integers. And then we have our non-terminal expressions, which are built up of sub-expressions. Okay, so let's now have a look at some commonly stated justifications for when to and when not to use the interpreter pattern. So if you need to interpret and execute expressions or commands in a domain-specific language, the interpreter pattern offers a flexible and extensible method for implementing the language's grammar and semantics. If your task only involves calculating simple operations that can be handled by general purpose programming languages or by a library, then using the interpreter pattern adds a lot of unnecessary complexity. So most of the time a general purpose programming language or library will do the job for you. And if the grammar of your language is complex, then the interpreter pattern could lead to having a large number of classes and increased code complexity, and in this case a dedicated parser generator or compiler would be a better option. So now we're going to take a look at why the interpreter pattern is rarely used. So Steve Yege, a software developer and blogger, says that the Gang of 4 book contains 22 patterns and a practical joke, and the interpreter pattern is that practical joke. So the problem with the interpreter pattern is that you must turn your language into an abstract syntax tree, and as you saw earlier with our calculator example, creating a parser or an algorithm for converting some input into an abstract syntax tree is a very difficult task to get right and is very time consuming. And for anything other than the simplest of languages, creating a parser is very difficult and likely to fail. So how did the Gang of 4 book deal with this? They basically ignored the parsing problem altogether and said that it was a separate problem to the interpreter pattern. So I've actually copied and pasted a paragraph from the Gang of 4 book about what they say about this kind of problem. So the interpreter pattern doesn't explain how to create an abstract syntax tree. In other words, it doesn't address parsing. The abstract syntax tree can be created by a table-driven parser, by a handcrafted, usually recursive descent parser, or directly by the client. But when we use the interpreter pattern, we have to somehow generate this abstract syntax tree. We can't just ignore the complex problem of parsing. And this is why Yege characterized the chapter as a practical joke, and why other programming techniques and patterns are almost always preferred to the interpreter pattern. And in your life as a software developer, most of you will rarely have to develop your own languages, so the other 22 design patterns will be of much greater use to you. However, there will of course be some specific good use cases for this pattern in the real world. Okay, so that's enough of this pattern. We're now going to move on to structural design patterns.